Today I will come to the gravitational wave we observed today. It's based on the transfer function that connects the solution here, where the tensor perturbation exceeds the horizon, and we already know that it will be a constant of order Hubble when it exceeds the horizon, and then it will go to let's see, P. To this value, re-enter the horizon and decay to what we observed today. So the evolution from here to here is described by the so-called tensor transfer function. Let's see, something like this. By solving the equation of motion of the tensor perturbation in this accelerated universe. And after doing so, we can use the knowledge we learned in the first lecture to define deep inside the horizon in this region. I mean, the energy density of gravitational wave, if you remember correctly. And the gravitational wave parameter. And this kind of thing is the cosmology used to compare with the observations, like the LIGO, LISA, and the pulsar timing array with different frequencies. This is the module gravitational wave. And also I will by the scalar perturbation inside in the inflationary era. That is from the curvature perturbation psi. Let's see. So psi will evolve. Similarly, it will become a constant outside horizon, and it will decay. Gravitational waves of the day. So this is based on the transfer function, which describes the evolution of the tensor perturbation we have for the late universe. Let me just write down the result we have from the previous section, that the primordial tensor perturbation power spectrum is something like this. This has a very weak dependence of the wave number. We can do it more carefully, but I think I will skip this part because the time is limited. And then I will directly go to solving the transfer function part. So in this case, again, we have to use the so-called auxiliary field, which is not, as I said, is the canonical variable in kind of quantizing the tensor perturbation. It's defined as VLK, remember. This is basically AHK divided by 16 pi g. If you like, you can write it in this manner. And then the equation of motion is V double prime and has a solution on superhorizon scales. So on superhorizon scales, H is a constant. This is something we already know, by the argument of causality. And this should be connected as I said, this solution is something we have in here. So it has to be connected with the inflationary value. And inside the horizon, the solution is a little bit different. So let's first consider the so-called long moving wavelengths. That these are the modes that we enter the horizon in the matter-dominated area. Let me just change this a little bit. It's for these modes. So in this case, you can just solve the equation of motion and get the following result. J, L, and L are spherical Bessel functions. And then you can use the asymptotic behavior when the argument goes to 0. So this is the case when it approaches the beginning, the end of inflation, or the beginning of the decelerated expansion. So you can immediately say that because we have this, so you can find that this is the one we need, because it goes to so this x to the, sorry, this goes to x to 1 divided by x, so it's a constant to be connected with hk from inflation. And the other one is not quite good, and it will decay as x to the cube. X is k, so it will just rapidly decay inside the horizon. So it just forget about that. So in that case, you have the solution that the hk is 3j1 eta, okay, eta of hk model. So this is just issue ramp with some coefficient. So you can see that this goes like on or A, and in the matter-dominated universe, A goes like eta squared. This is goes like k eta squared, but in the matter-dominated universe, A is eta squared, so it goes to 1 over A, as we expected. To calculate, we have to get some numbers, but I will just skip this part and go to the short mode. Short modes are these ones, these lines, let's see. So we enter the horizon in the radiation-dominated universe. So in that case, the solution is much easier. It can also be written in the zeros order Bessel functions. So again, use the asymptotic behavior. You find that this can be neglected, and the only one we care about is the first one, which is this. For scalar perturbation, usually this is just the case because a huge difference from the scalar perturbation and the tensor perturbation is that for scalar perturbation, usually we only care about the recombination epoch, where you can calculate the CMB, the impact on the temperature stuff. But for gravitational wave, as we observe it today, so we have to connect the solution here at a equality to today. So in this case, we have to use their solution in the matter-dominated universe, which, as I have shown before, is this one. I change the coefficient. This is the solution here. So this is the solution here. And in here, it is just constant, as we already know. So we have to, so this current value, it evolves like this, and it must be connected at this AEQ here. And then it follows the evolution of this, which is connected to this HK premodule, like this. And the content connected to the oscillation solution to the quantum fluctuation. This is what we are doing. So the next task is to determine the coefficient of AK and BK by requiring that HK at AEQ. Let's see, this is R, this is M. So they are both the same. And also, let's see, eta. Same time derivative. I will not go into details, but just show you the result. So in this manner, you can see that the so-called transfer function is just the this factor in the squared parenthesis is called HK of K8. Sorry, not just this, but also the time evolution. Just write it explicitly. The transfer function is AK J K eta eta divided by this K prime plus BK divided by HK prime N1. Okay, this is for short mode, which means that K is much larger than K equal. roughly speaking, this is this, but there is some kind of order one difference. Okay. So as a summary, I will just write it in here. So you have the transfer function that we put eta to today, so that we can connect this to the observation. For long wavelength mode, this is quite easy. And for short wavelength mode, I'll just copy it here. So the gravitational wave spectrum, the so-called gravitational wave parameter, if you can remember, it's defined in this way. So rho GW is something like this. The omega GW is the critical of this. Here the key point is that we have to expand, as I have shown before, that the Hij of x eta is something like this. Something like this, and you substitute the solution to here. This is just the T of k of eta, and the times the T of k of primordial. Let's forget about the difference between the two polarizations. And suppose that the polarization are the same. So then they share the same HK of prime, and you have a kind of a transfer function here. And all of this time derivative, the time evolution comes from the transfer function. So if you have a prime, then it's just a prime here. And you can write it down and move this back and move this out, and everything just goes into the direct definition. And you can calculate all the way down and make sure that you use this kind of relation correctly. For a different normalization number, this is also different. Let me just write it down without any further notice. Lambda. Anyway, so with this, and then you find that omega GW is oh, sorry, I missed the most important part. This is the tensor power spectrum, which, as we have shown, equals to this. So this is the observed value for the gravitational wave spectrum we observed today. And it is a little bit difficult to look at its behavior for this transfer function, because it is a little bit complicated. If you just look at here. But it is possible to find its kind of leading order approximations. For instance, if you look at the first line, and this goes to in the limit when this k eta is very large. This is always true because we are talking about some inside the horizon result. So this goes to k eta squared times some oscillations. So roughly speaking, it is just something like this. And a prime will give extra k because you have the oscillations with respect to k eta, of course. So then a prime means that a k here. So you have a k and some oscillations. That's the case. And now your omega GW is you can take the average outdoor of the oscillations, right? Let me just do it without any further comments. So k squared, you have 9 over k squared, it has 0 to the 4th. This is the final result for long wavelength. If you write it on the, let's say now you can transfer the k to the frequency by frequency is k over 2 pi. See, it goes like this until some frequency where it is determined by the wave number which re-enters the horizon at the matter radiation equality. Then it will be the second line of this transfer function in here. And we have to look at the coefficient in here and in here. And you can immediately see that first of all, both of these two factors, I marked red, behaves the same in the large argument limit. This is because JLOX or NLOX, they always goes like 1OX plus some cosine or sine something. Right? So this red box factor goes to k eta squared, some oscillations. So you have to find the leading order of AK and BK. And in the case when there is when this k eta EQ is also large, remember that this is the condition when we can use the second line of the transfer function. That this term is the dominant term because it is linear in this large number, and the other things are either suppressed by this large number or just a constant, right? So in this case, the gravitational wave parameter is let me just go from the transfer function. The transfer function is bk divided by hp prime times n1, if I remember correctly. So this is what is bk? k eta eq. It's k eta eq divided by hk prime times some k eta squared times some oscillations. And this goes to hk prime of k eta squared, eta equality, and oscillations. And t prime, because of this oscillation, something like this, is kt k. You cancel this k here. Remember, this is the key part. So we have an expression that is independent of k. Which means that the omega GW in the short wavelength mode is a constant. I mean, a constant with respect to the frequency. So we know that the omega GW just goes down like frequency to -2 with respect to frequency. Just erase that part. And then goes to a constant, which slightly lean a little bit down. I will talk about this later. And with some unknown behavior. So this part is approximately the frequency at equality, which means that the wave number at equality re-enter the horizon and then transfer to the frequency we have today. The number is around the 10 to -16 hertz. But unfortunately, this is a frequency that we cannot very easily detect. And the amplitude depends, of course, on the tensor power spectrum, P of H. So it's proportional to the so-called tensor to scalar ratio times a very small number that is the scalar power spectrum. Let me just like 10 to -9. So if you substitute this back into here and do some calculations, you will find that this is also around 10 to -6. And a little bit lean here reflects the slight dependence of the P of k here. So this is in some sense written in AT of some pivot scale, k over kp to n of t. So nt is very small. I forgot the Planck value, but it will be at most 0.1. Let me just write it. Oh. Something like that. I will just tell you some numbers to make this clear. This is the low frequency part. and the near constant part. Of course, all of these calculations can be made more accurate, and you can do it by yourself. There are some comments. Let me just draw the picture again here to make it larger. Oh, sorry. The first thing is that this value is far beyond the detectability of all of these current observations. Currently, the best thing is the positime array, which is at 10 to minus 9 Hertz. This is actually 1 year inverse, because the principle of the positiming is that we observe the time shift of different pulses from the millisecond pulsars, and use this different pulsars as some statistical time of arrival to get the change of the space-time. So in this case, the most sensitive frequency is to the inverse of the total observation time. That's usually that's in the unit of like 10 years. So in here, the sensitivity is something like this. Let's see. So this is 10 to minus 9. Maybe this is too large. And then if we go beyond, we have, let's see, this is 6, 12, 10 to minus 3. That's the sensitivity for LISA. And all of these space interferometers. The sensitivity is slightly weaker, but not quite much. And then it's the ground-based interferometers, like LIGO. The sensitivity is like 10 to the 6. It's almost comparable to the other constraints from the BBM or the radiation stuff. If we want to have the larger amplitude for the primordial tensor perturbation, as you look at this formula, a possible way is to change the inflationary model, especially the model of gravity, to make the NT positive. So NT is usually negative and small. But in modified gravity models, it is possible to make NT positive. Then this line can just go up and make it possible to be detected in the future, like in some next generation BBO or something. It is possible to do that. And it is also possible that we have some oscillationary stage at the end of inflation, where the equation of state is much harder than what we expect from usual quadratic m square phi square model. That is something we can observe from here. So as I have shown that in the inflation model, where you have the equation of state, effective equation of state, let me just write it in red. Effective equation of state is defined in this manner. So if it is oscillating, then this is just a 0. This is what we can expect from the reheating stage from m square phi square inflation. So in this case, you can imagine that the transfer function is the same as the one we have in here. So this will just go down, like in frequency -2. But it is also possible that we can have a larger tiered for the change of the equation of state. This is possible. If I remember correctly, that if you have a potential like phi to the p's, W is P minus 2 or P plus 2. For P equals to 2, then this just goes to 0. And P goes to 4. This is just the 1/3, like radiation. So it will just go this way, right? And surely it will go up if P is larger than 4. The best value is that P goes to infinity, which means that you have a potential that is exponential. So in that case, this W is 1, and you have a tiered that is proportional to the frequency squared, if I remember correctly, squared, or let me just check. I have the calculations in somewhere, but I don't want to go to details. I just want you to know that if P is larger than 4, then you can have some kind of a enhanced primordial gravity wave. The principle is very easy, that it is because in this stage, the background evolution of the energy density decays much faster than the radiation. So in that case, omega GW as a ratio of the gravitational energy density divided by the background energy density will just go up. This depends on the decay rate of the background energy density. If the background energy density decay faster, then gravitational wave energy increases faster. And also, please.
Sorry, yeah, please Swagat. So this is F, just F, not F square for stiff liquid.
Thank you. Yeah. I'm a little bit nervous about this. Yeah. Let me just put in here. Okay, in this manner, it also depends on the temperature where this oscillation starts. Let's see, it's the end of inflation point. So this is also very important. So if we have a slightly smaller temperature where the universe got inflated, then this point will just move leftward. For instance, as Swagat said, you have P goes to infinity, then you have a proportional to 1, something like this. And it just move left, move left, move left. It is indeed possible to be detected in the future by such kind of a scenario. Of course, you need some cutoff in the infrared. Otherwise, it will just increase forever. That's absurd. And also, it when it meets some bound, you can show it. I think I will leave this as a problem that the quantum fluctuations for the modes that never exceed the horizon will increase as the frequency to the 4th. But that is a fake mode that we have to reduce from the physical interpretation. I mean, if we go to the space-time diagram, I was talking about this kind of mode. So if you calculate omega GW of this mode purely, then you will find that this is proportional to the frequency of the force here. It's a huge divergence, but it's not physical. I will not talk about this in detail, but just to let you know. So we already
just a minute. When you mentioned that k power 4 behavior, that just corresponds to the Bunch-Davis vacuum modes, right?
Yeah.
Just the sub-Hubble modes that never leave the Hubble radius.
Yes.
So
yes.
the cutoff that you're talking about, is that coming from energy cutoff, or is there some other motivation?
There must. Actually, in some sense, this is basically the same thing. I mean, if you look at, okay, let me just come back to, let me just draw a new figure. So in this, sorry. So in this figure, I'm talking about this mode. But if you have an oscillationary feature, then it's something like this. You always have such kind of mode, right? And the more you increase for the gravitational wave due to the oscillations, the shorter the frequency, the smaller the frequency of this Bunch-Davis modes is. So you have to just cut it off before you meet it. If you just draw the picture as you want, so it may be something like this. So you go down and then you meet this mode, which goes up, so like it before. But you have to just reduce these modes because this is never physical. And if you have the model I talked about for the enhancement, because of the different equation of state and the low radiant temperature, it might be something like this. You also meet this, right? Maybe earlier, I forgot how depict that. But anyway, you have to always reduce this mode. Otherwise, you cannot interpret it as a physical gravitational wave. I think I will leave it in a problem, yeah, but I haven't finished that yet. Sorry, I will do it after I finish this lecture. Okay, so I talked about the blue tilted. The gravitational waves enhanced by a stiff equation of state after inflation. Now I will turn to the so-called gravitational waves induced by scalar perturbation. Basically, this kind of thing is always there because you have a first order perturbation theory, then you can go to the second order perturbation theory. You can always do that. But the key point is that in the leading order, there is no couplings between the scalar vector and tensor modes. That's the so-called decomposition theorem I have introduced. But if you go to next to leading order, there will be couplings. So the couplings like H phi, let's see. So this doesn't exist, but we go to the next to leading order, you have H phi squared, H squared phi, something, and with vectors and so on and so forth. And this can exist. So from this kind of coupling, you may imagine that your equation of the tensor position, let's forget about the Hij here, just H prime prime. This is at but it can also be of a system that phi is the Newton potential, as I always note. So the key point is that usually this Newton potential is very small. So it is of order to the curvature perturbation. So it's of order 10 minus 5. So why don't you just estimate? So if this is the case, then this h, small h, is just 10 to the minus 9. And we know that the omega GW is the power spectrum of h. Is, as I said, is a redshift factor times omega r times h squared. Let's say this is hc. And this is 10 minus 5. And we have 10 to minus 8 times, let's see. For primordial tensor perturbation, hc is h over mp. This is like 10 minus 5. Or even smaller, let's say 10 minus 6. So this, you have a 10 minus 14. So this is a overestimated. And for a scalar induced value, this is 10 to minus 9. Then you have 10 minus 17. So that's always difficult, sorry, squared. So that's always much smaller than the leading order value. So you don't have to take much care about that. So this kind of effect can only be important when the scalar perturbation get enhanced on some small scales. This is because the current observation on CMB and large scale structure can only constrain the scalar perturbation on very large scales from the around this recombination scale for about 2 or 3 orders of magnitude. If you go to even smaller scales, then basically there is no constraints. So if you look at, for instance, a constraint picture of the power spectrum, it is well constrained by Planck at the very large value. Let's see, so this is a 1 MPC for the T mode, right? And some not very good, but still okay constraints from the large scale structure. But if we go downstairs for about 5 or 6 order of magnitude, then you cannot have any serious constraints. The only constraints are that the scalar perturbation cannot be too large. Otherwise, you have too many of the primordial black holes that will spoil the homogeneity of our universe. So it is quite possible that we have some enhancement of the scalar perturbation on some smaller scales. It can be as large due to the constraint from PVH, let's see. It can be as large as 10 to minus 2. So in this case, you can have a comparable gravitational wave induced by the scalar perturbation. For instance, if you have it here, then hc squared, let's see, is the phi squared to phi to the 4th, 10 to the minus 8. So you find that it's basically the same thing. Yeah. So this is a very intriguing argument. And there is a coincidence that usually if you have the detectable amount of primordial black holes, The corresponding induced quantum wave is also observable in many of these frequency and mass ranges. For instance, the only window that the primordial black hole can be all the dark matter, which means that there is a window that you can just go up to where you have all of these primordial black holes that matter. Let me just draw quickly the picture of the PPH here. So the energy density of a primordial black hole divided by energy density of cold dark matter can be well constrained by some lensing experiments or so forth. But there is a window in here at like 10 to the 16 grams to the 10 to the 22 grams that you do not have any constraint. So the mass function of the primordial black hole can be picked here. And this corresponds from this curvature perturbation, let's see, Newton potential, to the tensor perturbation and to the gravitational wave, which is where inside the detectability of LISA. This is the induced quantum wave signal at around 10 to the minus 3 hertz. So if you move this peak around, then this frequency also moves around. But basically, it's always above the sensitivity curve. So that's the most interesting thing I have found in this scenario. So to do so, we have to study how this is possible to generate the gravitational wave by the scalar perturbation. I only have a half an hour, so I don't think I can go into details, but I just show you how to do that. If you're interested in this picture, you can go to the related papers and do these calculations by yourself. So the basic idea is you expand the metric in a conformal Newton gauge to the first order of the scalar perturbations but second order in the tensor perturbation. Of course, there is a first order scalar tensor perturbation, but we already know what it is. It is based on the quantum fluctuations from inflation, and anyway, it has an amplitude which is p squared, and so on and so forth. Everything is clear. But now we want to know the gravitational wave sourced by the scalar perturbation, and we try to expand the equation of motion to the second order. And so similarly, you have the energy momentum tensor. Blah, blah. I will not just write it. It depends on the first order of the peculiar velocity perturbation. And some perturbation of the anisotropic stress, which is proportional to this. How do I know? So anyway, the equation of motion can be written in this manner. So Hij prime is, as we said, this is a, we have to project it by this projector. The source term is so the first two lines of this equation comes from the left-hand side of the Einstein equation. It comes from the second order of the scalar perturbation. And the other parts comes from the right-hand side. It's the second order of the energy momentum tensor. So it is very convenient because we know that this is 0, that we can always set psi is -5, right? And then we substitute all of this into here. So you can find that the first two lines becomes just one term. Plus the second term. Plus some total derivative. So this is the source term we have. And for the total derivative, we can just neglect it because it's in the equation of motion. So in this case, we go to the Fourier space. Sorry. And remember that the definition of this can be written in a sum of two polarization tensors. And then you substitute this back into the equation of motion, make the Fourier transformation of the equation of motion. And this dots means this has the same structure as this one. So immediately you see that the both of these proportional to this one. We have a similar equation for the cross polarization, and then you do the inverse Fourier transformation to just drop off the k dependence on the left hand side. Then you have on the right hand side you have an integral like this. So this just give you the delta function. And you also have the integral of q. So this makes just q equals to k minus p everywhere. And the key point is that this ELM times the PL and the K minus P M is this. So this is 0, right? Because this is a kind of a transverse tensor. So it times Km, so it goes to 0, right? So we only have the second term. And this cancels this minus sign here. So we have sorry. Now I should write down the left hand side. I will neglect this plus sign because the equation is identical to both of the polarizations. Okay, of P, L, P, M. I just put it in the integral. Right. And this is just this one. This is the same. I write it in a more compactly. So in this case, it is very convenient to do 3 things. First of all, let me just mark it with 3 different colors. purple, yeah, and purple has three kind of thing. First thing in red, that this can be written in the transfer function of phi and its primordial value during inflation. This is what I have done in the previous two lectures. So I have to find out the solution of this, which is, if you can remember correctly, I didn't put the prime here because I suppose that the collision perturbation in comoving gauge is already primordial value. I never use that after inflation. So this is a y is k eta divided by square root of 3, the sound speed in the radiation. This is the first thing we do. And second, let's go to the yellow color. It's very difficult to read. Second is the deal with the angles. I have to use the following definition of the polarization angle that I define. This is a k direction, n direction, and m direction. So they have a Cartesian coordinates. So then you can define the Eij plus as MIMJ minus NIMJ. And then you can put it Eij plus the PL, PM equals to M, sorry, PIPJ. MIPI, MJPJ minus NIPI, MJPJ. Just look at it in this way. So this is M, N, P. So you have all of these angles, theta, phi. So MIPI is M dot I. So let's just write it M dot P squared minus N dot P squared. So this is a P sine theta cosine phi. The other one is P sine theta sine phi. So this is a P squared sine squared theta cosine squared phi minus sine squared phi. This is just cosine 2 phi. So Eij plus PIPJ is P squared sine squared theta cosine 2 phi. Ij cross PIPJ is, I will not do it. This is sine 2 phi. So then you can write the integral of the d cube p into the p squared dp d sine theta phi with these angles. This is the second thing. And then, after you do that, you can redefine this solution in here in the Bessel functions. So you get out all of this primordial value, and all of this phi here is just j on y over y divided by r times some constant. So you just you have In that case, the equation of motion can be reduced this function f is a combination of Bessel functions. U is k minus p divided by k. E is p divided by k. Okay. The next task is to just solve this equation. Now, this can be done by the so-called Green function method, given the source term. It's like this. This is the source term. So the solution is where the Green function satisfies this equation. And it has different solutions in radiation and matter-dominated universe. Which we needed is the one in the radiation-dominated universe. I'll write it in here. Something like that. So x is k eta divided by square root of 3. Prime. Okay. So you have the solution, and then you can substitute it back into the tensor pervasion. The key point is to calculate the 2-point function of that. That's the reason why we have to calculate the gravitational wave energy density. So hk eta hp eta is a squared not eta 2 not eta d eta 1 eta 2 Green function of eta 1 function of eta 2 of the 2-point function of the source term. Now remember that the source term can be written in the transfer functions and the primordial values. This is what I have shown. And it is connected to the angular part. I talked about. If you look at here, yeah, this is the source term, and I calculate by all of these factors, and by using this angular factor, we can get the angle out. And the promoted value is this one. So this is proportional to, let's forget about all of the angular part. View. Sorry. So then you have to do the splitting of this 4-point function into 2-point functions. So if it is a Gaussian, then you don't have to care about the non-Gaussianity part. It is just a summation of two of this 2-point part. Which are basically the same thing. So I will write the power spectrum in a slightly different manner, that the power spectrum of RL and RQ is a 2 pi cube delta L plus Q over P of R. So note that this is different from this curly P of R, which is defined as 2 pi squared of K cube. Curly over. It is just for convenience. Otherwise, you have too many of these K cubes. So after adding all of these terms together, I will skip the discussion on how to integrate the angles. That's a little bit difficult, and you need to pay attention to that. But it's worth doing if you're interested in such thing. I will just write down the final result written in the power spectrum of the tensor perturbation. Note that this is connected to omega GW. Prime means that get rid of this delta function. So this is This I square UV is something that you can integrate it for the time evolution. So it's roughly speaking, it's just something like this. All of the time evolution. You still have the time evolution in the f function. I will not write it here, but I will just mention that this is something that is connected to U and V. So it's basically it's over the one. So then you can use this equation to calculate the power spectrum of the induced quantum wave, and after that you can calculate the gravitational wave parameter by just in this way. Now we do not have any transfer function dependent because all the time integrals are just reflected in this expression and is integrated out. I will not go into the draw some pictures for that. So for a delta function peak that is often frequently used, that the power spectrum of R is AOR of a delta function. Okay, this will give you an analytical result, but you might have or have seen it somewhere that it goes to something like this. It's omega GW of K. So the peak is a 2 over square root of Kp. So this is this Kp, and there is a cutoff at 2 Kp. This is because the momentum conservation. So this peak is a kind of a logarithmic divergence. So in some sense, it is a kind of a fake divergence because you cannot have infinitesimal width of the peak in the curvature perturbation. This is not so correct. So for a more realistic model, where you have a finite width peak, in for instance in logarithmic, region, then this peak will become a little bit broader, but steeper in the infrared. This goes to K squared in the delta function case, and change the color, goes to K cube. In the finite width color. And this kind of peak becomes more and more smooth as the width increases. Let's say, so this is sigma equals to 1/2, for instance. And for sigma is equals to 1 is something like this. And this can be very easily understood by just looking at this thing. So roughly speaking, as I have estimated that the GW is some kind of a 10 to minus 2 factor, and this is because all of the coefficients times the omega r naught. This is 4.2 times 10 to minus 5. The current value of the omega GW. So let's just make h squared. H is like 0.7. Hubble is 100 h kilometer per second per MPC. So let's make it in this way. So times this times the per module scalar propagation squared near the peak. This is always the case. So in this case, you have an estimation for this manner. Please be careful that in this case, the normalization of the peak is 1. So this means that you have this normalization. So the coefficient is proportional to AR over sigma, right? So in this case, h squared omega GW is, let me just use all of the numbers, 4 times 10 to minus 7 times AR over sigma squared. And it also has a Gaussian distribution because the Gaussian distribution is here. And then you also have exponential minus kp squared divided by sigma squared. There is a number 2 missing because it is a square of 2 power spectra of the scalar perturbation. So in this manner, you can by looking at the figure of the scalar perturbation and the tensor perturbation, you will find that the tensor perturbation peak becomes narrower because what I want to say that omega GW is sigma divided by square root of 2. So in the infrared, it still goes to k cube, but in here, it's just exponential. And with the amplitude, 10 minus 7 times A of sigma squared. As I said, for instance, A equals 2 times minus 2 corresponds to the primordial black hole. That's the primordial the requirement of primordial black hole formation. And we suppose that for a typical model, that sigma is 1. That is quite typical in the inflation models. In this case, you have this peak value, and the GW peak is 10 to minus 11. It's still difficult, but not too difficult to be detected. For instance, in the future experiment of SKA or something. Can be turned a little bit larger to make more primordial black hole formation and larger induced correction waves. I think I will just stop here. And for more details of the induced square wave, you can refer to some recent papers. I might also put in the problem sheet.
Yeah, thanks, Shi. So there are some questions. I think Raghavendra, you want to ask the question?
Yes, this is regarding the slide that is showing the integral that is given for pH. The pH as a double integral over the power spectra. Hello.
Oh, sorry. Let me just
okay.
share the screen again.
So I just wanted to ask, related to the previous comment, the integral is a double integral over momentum space, and it goes all the way to infinity. So are we accounting for those sub-Hubble modes as well? Because sub-Hubble modes have
okay. Actually, in this case, we do not care about the both the infrared and the ultraviolet infinity divergence because usually, as I have commented, the power of the scalar perturbation is peaked. So we only care about the peak. There is not a kind of a cutoff put in by hand, but a Gaussian distribution or some other distributions can easily just read off all the related modes just around the peak. If you have, instead of a peak, you have a power law, then you do need a cutoff. That's true. That's not only for such an induced square wave model, but for any other models, you do need that. And otherwise, a non-zero spectral tilt will always either in the infrared or in the UV. Yeah.
Okay, and related to this second order perturbation, if we are considering the 4-point correlation, for instance, the RR that we calculate to account for in the source term, shouldn't we also be concerned about the cross correlation like RRH? the tensor scalar correlation, because the second order tensor is proportional to roughly r squared, and that scalar tensor correlation will also be proportional to this 4-point correlation that we are calculating. So is that a valid concern?
Right? Scalar perturbation is what we usually observe. We usually consider, because that is the largest term that can source gravitational waves. Is that your question? I'm sorry,
No.
I was distracted by the connection.
Okay, I was just asking, we are considering the 4-point correlation of the scalar perturbations for getting the second order tensor power spectrum. So the same 4-point correlation will also come into play when we calculate the scalar tensor correlation, given the tensor is now second order. So can we expect a
scalar tensor?
Yes.
Scalar tensor perturbation.
Yes, scalar tensor correlation, now calculated with the tensor at the second order, will also contain this same expression. So can we expect the amplitudes to be roughly the same? The cross correlation and the calculation that we just did.
You talked about the scalar tensor coupling, right?
Yes.
And then you calculate the tensor 2-point function. Is that the same with the induced current wave? I cannot see any difference. The induced current wave is the 2-point function of the tensor perturbation. And each tensor perturbation is sourced by a quadratic order of the scalar perturbation. So it's the tensor scalar. So 2-point function of tensor is the 4-point function of scalar.
Yes, yes.
And then you into 2, so it is the product of 2-point function of scalar. And that's what I talked about.
Hi, Shi Pi. Since we discussed about induced gravitational waves, second order, so would you like to comment about gauge issues? Maybe briefly.
Gauge issues.
Yeah.
Oh yeah. That's something I do not have time to cover. Yeah. As you might know that we already know that the at first order or leading order, the tensor perturbation is gauge invariant. Let me just share my screen. I hope you can learn from what I have shown before. That's something 2 days ago for the gauge issues. I might have lost. Oh yeah, it's here. Great. Yeah, I just want to show this. This is this doesn't change in this infinite symbol gauge transformation we have imposed, and this is because that is already in the TD gauge. So this is the leading order. But as we know that in the second order, this HLJ has some terms coming from the first order scalar perturbation, which is indeed gauge dependent. So as you can see from the solutions, that in the solution of the Newtonian gauge, it is completely written in the first order scalar perturbation of the Newton potential. So there is indeed some gauge dependence in there. And this is some work that some many authors are discussing in the recent 2 years. And I think there is one common sense that we cannot just say something, define something that is gauge invariant and discuss the gauge invariant second order tensor perturbation. I think that's not appropriate. Maybe you can do that. You can define the combination of the gauge invariant quantities to the second order. But the key point is that how to interpret it with the observations we have, especially how to define energy density from the second order tensor perturbation. That's the key point. So in this knowledge, in this logic, we do not have to pay much attention about constructing the gauge invariant issue. But if everything can go back to the Newtonian, how can I say, to Newtonian approximation, it should be fine. I think that's the basic achievements of the paper written by Dominic and Sasaki. So that's
What would happen?
their main result.
Now, suppose we compute it in a different gauge.
Yeah.
Would anything change as far as the detector is concerned?
Mm-hmm.
Now, suppose I do
Sure.
all the calculation in a different gauge.
Yeah, surely it depends on the gauge,
Yes.
of course.
Yes. So,
omega GW will be different in different gauges.
yes.
And so in some gauges, it just diverges.
Mm-hmm.
And currently, we know that in some gauges, we call good gauges, the omega GW just converge when time flies.
Mm-hmm.
And then all of these good gauges converges to the same answer. That is the Newtonian gauge, the synchronous gauge, and something that we believe that this reflects the quantity we observe in the interferometer, and the definition of the energy density from this gauge reflects the nature of what we have discussed in the short wavelength approximation. But some other gauges, like the common gauge, we believe that is bad because the omega GW or the energy density of omega GW of rho GW just diverge as time flies. So we believe it is bad. The reason it is bad is that inside the horizon, it is always very difficult to choose a gauge that commoves with the coordinate.
Yeah.
So if you commove with the coordinates, then the information is just gone. So that's something that depends on a physical point of view. It's not just a coordinate choice. It depends on the physics, which quantity in which frame you are measuring. That's important. I cannot say that I completely understand this gauge issue, but I'm still trying to understand that. It's a good question.
Thanks, Vipul. Yeah.
Yeah, thanks. So there is a question in the chat box from Said Naqvi. Do you want to speak up, Said?
Yeah, hello, am I audible?
Yeah.
Mm-hmm.
Yeah, hi sir. Thank you for the lecture. I was just wondering, like, when we are studying these primordial gravitational waves, so are they studied from so from some exact solution point of view? Like right now we've studied as perturbations to FLRW metric, but are there any exact solutions being studied which involves such kind of primordial gravitational waves?
What do you mean by exact solutions? We always have to do the perturbation theory, right? The gravitational wave is defined as a perturbation to the background metric. If you cannot do such kind of a splitting, then you cannot define any gravitational wave. I think this is what we have discussed before in short wavelength approximation in here. Yeah.
Mm-hmm. So
if you look at this, if you look at this, it is very important because the only way that you define a set of gravitational wave is that it has a completely different frequency or wavelength with the background, and the amplitude is smaller. It's both either one of the wavelength or frequency and the amplitude is important. So if any of these condition doesn't apply, then you cannot define gravitational wave. That's very, very dangerous.
okay, no,
For instance, if in a circumstance that the oscillation is the same as the background, you cannot have any gravity. For instance, if you just move inside the binary of two black holes, and you ask yourself that how much is the gravitational wave amplitude there, and then I believe you cannot get any reasonable answer, because the change of the space-time is so severe that you cannot split it into background and wave.
Okay, maybe I confused because there are these exact plane wave solutions, right? Where the gravitational wave nature is sort of inbuilt in the metric. But as you said, I guess we need like perturbations over here. So yeah, okay, thanks.
Yeah. Okay. Thank you for the question. It's Wakat?
Hi, Shi Pi. I have some comments and questions about the blue tilted part. Can we go to the plot of omega GW versus frequency?
Okay. I have drawn it for many times. Okay, let's just stay in here.
Yeah. So suppose we talk about the infrared.
Oh no, this is with us time. Sorry.
Yeah.
Sorry, this is
yes.
This one. No.
Yeah. So suppose we think of blue tilted gravitational waves from reheating, not from reheating really, but entering during reheating. So infrared cutoff would be valid if the equation of state during reheating is one equation of state. But it might happen that the equation of state, because of the complicated physics during reheating, it has two different values for two different times. Then there may not be any necessity for infrared cutoff, because it can rise for a while and then it can fall after a while. Right? I think we had discussed this once long before. But look at this red line, which is increasing towards LISA sensitivity. The leftmost line. Okay. Now it may happen that around the time when it is reaching LISA, it can start to fall. Like it can start to have a red tilt after that, because reheating is complicated. Right?
It's oh yeah, you are talking about some primordial blue tilted, but with the normal reheating, like it just decays K to frequency to -2.
It is blue tilted for a while, and then it decreases with frequency, depending on what's the equation of state.
Oh yeah, sure. Like for instance, you have a quadratic potential, then then it just goes down like this.
Yes.
Yeah.
So
it depends on the depends on the reheating temperature. In here, I think it's around 100 GV, something like that. Maybe smaller, 10 GV, 1 GV. Yeah, sure.
Yeah.
If you have low temperature reheating, then yes, everything is fine.
Yeah. And the second comment is just a very minor comment. I think the LISA sensitivity you have plotted here should be much lower.
Much lower? Okay.
You have around 10 to the power -8. It should be around -13 or something.
Let me check this paper by Green and Romano. Oh yeah, you're right. 10 to -14.
Yeah, it should be lower. Yeah. So.
Yeah. That's great.
Yeah, I see.
It's very happy to know that it is possible to detect such kind of a linear things in the future.
Yeah.
Thank you for pointing that out.
Yes, thanks.
I just see there are no more questions in the chat. I think then we are at the end of the set of lectures. So thank you again. I mean, on behalf of all the participants and the organizers, let me thank Shi for all the hard work and the wonderful lectures. So thank you so much.